Welcome back, everybody. By this point in time, we're already pretty familiar with circles and a lot of the objects associated with them. We've defined a circle as the set of all points, called a locus of points, that are all a particular distance away from the center. That distance, and the segment whose length is that distance, is our radius. Beyond radii, we've talked about segments whose endpoints lie on the circle. We call those chords, and a special chord here, BD, which is a diameter of the circle because it runs through the center of the circle. A diameter, of course, is just a special type of chord. We've also talked about angles like the one I marked, DCA. These we call central angles because the vertex is at the center of the circle. Further, we've talked about portions of the circumference of the circle, and we've referred to those as arcs. And of course, we have one particularly special kind of arc. That's an arc that is intercepted by an angle of 180 degrees. We can also call that an arc who's intercepted by a chord that is a diameter. And that's just a semicircle. We've discussed the various theorems involving these objects, the measures of arcs, the lengths of arcs, the measures of central angles. But now we're going to get on into a topic that's one of the favorite habits of most geometers. It's a concept called inscription. You'll usually hear about it as inscribing things into a circle. When we talk about inscribing, all we mean is that it's something inside the circle whose vertices are on the circle. As a result, we can talk about inscribed angles and inscribed polygons. Let's deal with angles first. We can simply define an inscribed angle as being an angle whose vertex is on the circle. So angle BCA in circle C that we've already drawn, we know that's not an inscribed angle. That's a central angle because its vertex is the center of the circle. It lies within the area of the circle, but not on the circle itself. So let's take these three circles I've prepared for us below and talk about what it means to inscribe an angle in them. Well, we might as well start by naming these circles. Circles P, Q, and R. Now let's draw some inscribed angles. ABC is an inscribed angle in P, since B, the vertex of the angle, lies on the circle. In this case, you'll notice that P is on the interior of the angle. Here's another circumstance. Another central angle, but this time the center is actually on the angle. Well, certainly we can think of a third case here as well. This last case, where the center is on the exterior of the angle. I only bring these up because these are incredibly important figures in proving the next theorem. We can notice in each of these cases that each inscribed angle intercepts a particular arc in the circle. So inscribed angle ABC intercepts arc AC. But we have two more objects that we can actually use to intercept the same arc. Most importantly, there's a central angle that intercepts the same arc as well. And indeed, if we wanted to, we could draw in chord AC that would also intercept arc AC. But what we need to note here is that there's a special relationship between the inscribed angle that intercepts a particular arc and the central angle that intercepts the exact same arc. We can speak about that relationship with the following theorem. So the inscribed angle will always measure half the size of the central angle that intercepts the same arc. So if we happen to know in this case that angle APC measured 150 degrees, this theorem would tell us that inscribed angle ABC would have to measure half that, or 75 degrees. This is a very simple relationship, and it makes doing some algebra with circles incredibly easy. But I don't think that we should understate how kind of incredible this theorem actually is. That wherever I place B between A and C, that angle will measure 75 degrees. If B had been where B prime is, the measure of angle ABC would still be 75 degrees. If B had been where B double prime is, the measure of angle A B double prime C would also be 75 degrees. It seems a little bit counterintuitive. And in fact, in order to prove it, we're going to have to prove it in each of the three cases that we talked about before, where the center is on the interior, where the center is on the angle, and where the center is actually on the exterior of the angle. This might be a pretty long proof if we try to prove all three parts. I think that the first one is the easiest to prove, so we'll skip that one. Let's take a look at the second case, where the center is actually on the angle. Let's prove that it will be the case that the measure of angle DQF will be twice the measure of angle DEF. This is kind of a funny looking scenario. In the case of the first diagram, we can see that triangle congruence might help us, because we could draw in radius PB and perhaps find congruent triangles. This situation seems a little bit stranger than that one. Let's see if we can take this diagram and actually prove that the theorem we've written down must be true in this case. Here's a close enough approximation to the original diagram. And here's all the information that we know. We've got a circle, we have an inscribed angle, and we have a central angle. We would love to prove that that inscribed angle is half the measure of the central one. Here, of course, I've written that the central angle is twice the size of the inscribed angle, which says the same thing. I've moved this diagram down so we can do a little bit of work below the given and proved statements. Well, we have a triangle here already, but I think it's always a good idea to finish off any triangles that are in a circle. Now we've created triangles EQF and triangle DQF. Though we have quite a bit of information about some of the segment lengths involved in these triangles, for instance, EQ, DQ, and FQ are all congruent because they're radii, I don't think we're going to have enough information to prove that these are congruent triangles. In fact, just by looking at the diagram, we can see that they don't have to be congruent angles. Perhaps we should go back to some more fundamental ideas having to do with triangles and the sums of angles. I'm thinking of a theorem and a postulate from long ago that I hope you remember. Perhaps we haven't seen these for a little while, but they're always pretty handy. The Triangle Sum Theorem can actually give us almost all the information that we need. But let's not forget what we observed before about these radii. These are all congruent, which means we've just created two isosceles triangles. That being the case, angle E must be congruent to angle QFE. Likewise, angle D must be congruent to angle DFQ. So now we know that we have two congruent angles in each of the triangles we've created. The Triangle Sum Theorem allows us to write two pretty important statements. Take a look at these two statements and make sure they make sense to you. Since the sum of the angles in both of these triangles have to be 180 degrees, and we know we have two congruent angles in each triangle, we can take each of those congruent angles, multiply it by 2, and add the remaining angle to give us 180 degrees. In the second case of the linear pair postulate, we know that the two angles with vertex Q have to sum to be 180 degrees, since ED is a diameter in this case. The thing to notice now is that within each of these statements, we have some of the angles that we care about. DEF appears in the first statement, and DQF appears in both the second and third statement. Here's what I'd like to do. Since DEF only appears in one of the statements, let's see if we can get DEF and DQF into the same statement together. And I think we can do that by manipulating this statement in pink. Now we notice that EQF is both in this statement and in our statement that already has DEF. We can do a substitution of the purple portion of this equation for EQF in that first statement. That allows us to rewrite that first statement as this statement. Since we're seeking to find the relationship between the measures of angle DEF and DQF, let's see what we can algebraically do to this expression to make that comparison as clear as possible. Well, we've got a lucky break right at the beginning. 180 degrees appears on both sides of this equation. Let's just subtract 180 degrees from both sides. That simply cancels them out. Now we can simplify this expression. Well, it looks like we're almost there. If we want to compare them, we might as well get dqf onto its own side of the equation. Let's add it to both sides. And this, if I'm not mistaken, is what we were just trying to prove. Let me make all of this a little bit smaller so we can see this work in total. So beginning with the information that the center of the circle Q lay on one of the sides of the inscribed angle DEF, we showed that the measure of the central angle, DQF, that intercepts arc DF had to be twice the measure of angle DEF, the inscribed angle, which also intercepts arc DF. So in this case, we've proven that the theorem here must be true. There are two other cases left to prove here, of course, to prove the entire theorem. But hopefully I've given you inspiration to figure out the other two. There's actually another interesting result coming directly from this theorem. Consider these two angles, both inscribed in the same circle. Even more importantly, they both intercept the same arc. Is there anything special we can say about these two angles? Of course. They have to be congruent. Let's consider for a second that they both intercept arc AB. The measure of arc AB has to be the same as the measure of any central angle intercepting arc AB. But we've just figured out that the measure of an inscribed angle is half the measure of the central angle that intercepts the same arc. Since there's a direct relationship between the measure of an arc and the measure of a central angle, that relationship has to extend to any inscribed angle that intercepts that arc. Let's say the center of this circle is point P. Then angle APB has to have a measure that's twice as large as the measure of any inscribed angle that intercepts the same arc. Since angles ADB and ACB both intercept arc AB, they have to follow the theorem we just proved. That is, they have to have half the measure of angle APB. And since angle APB has the same measure as itself, good old reflexive property, it must be the case that both of these inscribed angles are congruent. So for instance, if the measure of angle ADB is 35 degrees, we know that the measure of the central angle APB has to be twice that, 70 degrees. And if the measure of angle APB is 70 degrees, then the measure of inscribed angle ACB has to be half that, in which case both inscribed angles measure 35 degrees. You'll see a lot of algebraic problems that rely on both of these theorems, but for right now, keep thinking about a way to prove this second one. We'll come back in the next video and see two more theorems about inscribed angles and shapes. Thank you, everybody.